All right, so we take this linear algebra and apply it to differential equations, with systems of differential equations. So that part is how to produce the matrix is very easy. Okay, so that's what happened here. So the right hand side of our differential equations is assumed to be linear, and therefore so you have x and y appearing with the coefficients. So we're looking for ax plus by, ax plus by, cx plus dy. So that's what we're looking for, and those four numbers are the coefficients of x and y. That's what makes the system linear. The right hand side has only x and y appearing in a linear fashion, and therefore there are four total coefficients, and those four coefficients are put in the matrix, and that's your linear operator. Okay, it's not to forget what the meaning of that thing is. It is indicating the direction of our motion. Here somewhere, the direction in which we are moving as we know where we are. So once again, our location is given by the vector x. Then under the transformation, we end up with ax, which is attached to where we are and pointing in the direction of our motion. And once again, this is the picture that describes how we're going to use this analysis of eigenvectors. So if it is not an eigenvector, then generic behavior is at the top, and we are moving off our line towards the origin. Okay, if it is the eigenspace, okay, then the directions coincide, and therefore we keep moving in the same direction. Okay, so unless we're moving in the opposite direction, which is simply the negative eigenvalue. Okay, so with that in mind, so we produce the matrix very quickly, and then we analyze it in that fashion. Okay, so this we just did, and the analysis is sometimes more. You can do more than this, but basically it's the same. Number one step is finding eigenvalues. When it is linear, I'm sorry. So when it's a diagonal matrix like this, then the diagonal entries are the eigenvalues, so you don't have to do any work. So 2 and 4 are the eigenvalues. That's it. And then you already know that once again, that's the very quick step to the next one is that the exponential growth is, because both the numbers are positive, we'll have exponential growth in all possible directions, but not along straight lines. The straight lines are only along the eigenspaces. Okay, so in this case, because x is separate from y, then the directions are x and y axes. They are those so each population grows separately. If they are combined, then the growth follows these kind of parabolic trajectories. When the elements on the diagonals are equal, so in this case they are 3 and 3, so it's 3, 0, 0, 3. So then these are not parabolas anymore, they're straight lines, and therefore we have our fountain kind of thing. So it starts slow and then accelerates down faster. It is not, so it's not a, yeah, so to be clear, not this one. Why not this one? You can guess probably. Can you guess why not? It is a fountain, but does not match the conical type of fountain, because you see why it cannot be the case. Or frankly, no shape might work, even though characteristically the qualitative analysis is correct, but it cannot behave this way. It cannot, if it is under the force of gravity, it cannot accelerate exponentially. How does it accelerate? Under gravity, what kind of dependence on time?
Linear?
Well, yeah, quadratic. Yeah. So gravity, it is only quadratic. So in other words, kind of slow, and this is exponential. Okay, so accelerates exponentially. So it's not a fountain, but well, I don't know what this is. It's because there's some kind of pumping. It doesn't matter what the shape is. You try to accelerate faster, but you cannot accelerate faster than the free fall acceleration. So you cannot go faster than g. So you can. There's no way you can produce exponential growth here. So exponential here, quadratic there. So that's the mismatch. But it makes it more productive to think about population. So that's who changes exponentially? Populations, either decay or growth. And remember the other examples once again where it might work. It is maybe decay, radioactive decay, or heating, cooling, stuff like that. Okay, so once again, what I just said, lambda 1, lambda 2 are visible on the graph. Once again, where they have a negative, they are the same sign, the opposite sides. And that's the difference between unstable, stable, and semi-stable. So what we have accomplished, though, with our linear algebra is now we do not have to concentrate entirely only on the only our eigenvectors parallel to the axes, but rather now we are able to deal with any one of them, but then the conclusion nonetheless remains the same. The conclusion here is that the behavior along the eigenvectors or within the eigenspaces is exponential, one or the other. But it remains true for every eigenvalue, even if it is off. So there is nothing special about the axes. It just happens to be the simplest model where they off. So that's the major statement that we make. If we have eigenvector, eigenvalue combined together, and then this is the solution is, as you can see, if you carefully take it apart, then you can see that your solution is actually okay. I see what my little bit of problem here is that I want to make C lowercase because C is a number. Okay, so to separate the two vectors from numbers, then you realize that x is a vector, but it is variable of t. X is x of t, right? But as far as direction is concerned, it's the same because it does not depend on t. And then what does depend on t is the magnitude of the vector. So you multiply your v by this number, which may be growing depending on lambda. And then you end up with a bunch of solutions, but they're all pointing in the same direction along V. So if V is an eigenvector, we're never leaving that eigenspace. Okay, and so once again, it is nothing but a scalar multiplication. They're shrinking of the and reversing possibly of the vector. Nonetheless, it never will take off the solution of that line. Okay, so the solution is fairly simple. We call them characteristic solutions. Okay, and they are the simplest one. Once again, straight solution, of course, the simple one. And then these are the examples. When we're really lucky, every one is a straight line solution. But that's the degenerate case. Otherwise, these are the solutions. Both of them are positive, so they're running away in this fashion. So these are the characteristic solution in this for the initial example. Okay, so now we are not concerned with the x's. We have the algebraic tool to find the eigenspaces. And then once you do, we also have a theorem of how to do linear combinations of the eigensolutions or characteristic solutions to produce any solution. So that's what it is. If you look carefully at initial solutions are here, characteristic one, characteristic the other, and then you kind of do a linear combination of the two producing more solutions, and they look like, because of they going one in and the other one out, the end result is this, and the behavior is kind of, once again, we call it hyperbolic, because it's kind of like a hyperbola, right? So if they're, this is definitely hyperbolic. Right. This is what the hyperbola looks like. 1x is the hyperbola, but we think of it only when the aligns with the axes. But that's also very similar, like this. So from one line towards the other line, and so we have asymptotic behavior on both ends, and then so we still call it hyperbolic. So once again, so to summarize how we get it, we get two eigenvectors, eigenvalues. The two eigenvectors are not multiples of each other. Okay, so that's the key for the picture to be like this. like the two directions are not aligned. Otherwise, there is no linear combination to utilize. But if it is the case, then this is how we write the answers. And once again, if once again, let me make the lowercase to emphasize that these are the just constant numbers. And so then there are two parameters. And then so we push a little bit more in the one direction or the other direction, and then we have some kind of a parabolic hyperbolic behavior between the two eigenspaces. So so once again, this might be E lambda 1 and E lambda 2, and they look like this. The two spaces, and then everything else happens in between. Okay, so we algebraically can explain what it is, and there aren't too many things that can actually happen. So that's why we are able to actually continue on and classify the linear systems based primarily on that. But we're still limited to, that's the caveat, real eigenvalues. So complex eigenvalues coming up. Okay, so so here once again I'm using the same, pretty much the same ones that linear operators that we have had before, and we have analyzed them. And so but the jump is new, but not really that as you can see, it's really not much of a challenge. So I have 1, 2, 2, 4, and I just put them automatically quickly in my matrix, and that's my linear operator. And then everything else is simplest algebra of the high school level. Okay, so as you can see here, it is done by the spreadsheet, right? So this is the computation. You can see how the plugging in this matrix into the spreadsheet, it computes the eigenvalues, and it happens to be 0 and 5. Okay, how do we know why is it 0? Do you remember that 0 eigenvalue is the effect of a projection? And how can we detect the projection? It's another one is the determinant is equal to 0. So that's another way to just make the same discovery. So determinant is 1, 2, 2, 4 is equal to 0. You know that there is a projection, and then you realize that there's actually dependence between the columns. You multiply first column by 2, you get this. The other one, that's the dependence between the columns and rows of the matrix, indicates a projection. Okay, so and then indeed these are Euler's solution, to be clear. So we haven't solved the problem. So these are Euler's. Okay, and then as we did before, and they incline. So the only question becomes whether exactly these lines, the particular direction. Remember, they never converge, so these are parallel lines. What is the direction? And the answer is, once we know the eigenvalues, we know that there will be a collapse in the projection in the direction perpendicular to these lines, and that line is the one that corresponds to eigenvalue 5. Okay, so well, we go through, just plug in the values. Yeah, so this is how you can discover it. Probably by now is a kind of an ad hoc, and we prefer the standard way with the characteristic equation. So let me jump straight to that. And so I'm forming the my matrix of a characteristic, and its determinant is the characteristic equation, the solution of which is the eigenvalues. So as you can see, this we set it is equal to 0, and then we discovered two lambdas. One is 0, that's the collapse projection, and lambda equal to 5, that's a stretch. So then we know that along one of the vectors it will be stretch, and this one, and along this one will be the collapse. So then what we do here is we need to find the eigenvalue, at least one, and then this is we just know that if we know that lambda is equal to 5, it's supposed to satisfy this equation right here, and we need to find x and y, at least one pair x and y producing the answer that we're after. And then once again, algebra that we have done before, discovering that y is equal to 2x. In other words, that's literally a line. That goes like that with slope of 2, and that explains what these lines are. We could have guessed that they might have a slope of 2. Okay, so the slope of 2, and then then pretty much the qualitative analysis is over, because there are these lines, and we can say that it's a lot more than qualitative analysis. We know these special directions, and we also know what's happening within each of these special directions, and that is exponential growth. Okay, so if you zoom in, you can see that the acceleration accelerates from this. So these are, let me mark these as I did before. So these are special points. These are stationary points. Stationary point, and then the rest of the solution run away from that in perpendicular direction with acceleration. Okay. So that all we acquired all this information from the linear algebra and that last theorem that we've had. And then, so if you want algebra written for the rest of the solution, that's what it is. Okay, so constant vector rather. Once again, let me put the lowercase here to make that point clear. And then so multiple of vector of which vector, this vector plus which is, it stays the same. So this indicates which line, which of those lines parallel to each other that we are on, and then this indicates how far along that line. Okay, so well, that's all there is. It has been solved. It has been solved in this kind of linear algebra manner. Okay, so so the saddle points we just saw last time. That's once again that's the thing. We find the eigenvalues first, then eigenvalues happens to be once again algebra determinant of a matrix 2 by 2. We solve it with the quadratic formula. Happens to be one lambda is negative, the other one is positive, so there will be exponential decay along one of the lines, this one, and the exponential growth along all the other. So once again, going through this algebra, it takes some work, but nonetheless, as you can see, the spreadsheet does that. And so we find out that one of the lines is going x equal to negative y, and in other words, the vector is negative 1, negative 1, and the other one is okay. So and then based on that, we write our solution. Once again, as you can see here, it is proportional, but varies proportionality to that vector v1. So we take a vector v1 and then we multiply it by the exponential function, which is simply the stretching coefficient of v. So that vector v is variable in length, but not in direction. Okay, and because lambda 1 is negative, there's the whole thing goes to 0. Okay, think about this. And in what way it goes exponentially goes towards 0. So the exponential decay along the vector along this direction. Okay, so that's you can see the arrows going towards the origin. So my origin is here, and the solutions are going this way in a decelerated manner. Okay, the other one you pictures, once again, this is Euler, so we can predict everything from Euler's solution. What's going to happen? They are running away from the origin in an accelerated manner. Just to exactly find the vector, which has been found by Excel already. So we just solve the same equation. Once again, we end up with x equal to 2y over 3, and then vector is 1 3/2 is our one of the eigenvectors, and there's the two eigenspaces are go on the right. So once again, this is lambda equal to -1, and this is lambda equal to 3/2. What is it? What's my equal to 4? Okay, and so the arrows are quite descriptive, as you can see. They show which way we're going, and then the rest of you could do Euler, or imagine that you don't have the computer with you. This is we have discovered by hand. So then you can plot it by hand, the lines, and then by hand you can plot. So once again, this is by hand. You can plot the curves, because you know that on one hand we are running towards the origin, and just next to it we are running away from the origin, which means how can it happen? It happens like this, in and then out. And that's drawn by hand, these orange curves. Okay. It is asymptotic behavior. Once again, the solution within each of the eigenspaces is simply exponential functions, which I already pointed out. So so number one for the second one is this. For the first one is that. Okay, so and then first one converges to 0. This one is the opposite, goes to infinity. And then we just do linear combination, and then the problem is solved in an algebraic fashion. As you can see, this is probably the most revealing. So it is a linear combination of two vectors fixed vectors, but the coefficients vary with time, and that's what creates a curve. So once again, I like these to be lowercase, even though we're so much used to having uppercase for that plus C business. But probably by now we should be past that. Unstable equilibrium, because we have running in and running out. And so once again, if you remember that I made a better picture last time, it is the another description is settle point. So the what's on the right is the view from above on a settle point. Settle point, once again, so roughly speaking, what it's a settle. So either you think mountains or you think settle. So there's a horse, and this is here where its head right here. This is its tail, and this is your right leg, and this is your left leg. Okay, so your legs are on to the left, to the right, down, and then head is up, and the well, it's not much of a tail, it's more of the butt is going up. That's the settle, right? So going down for your legs down, and for the rest is the actual settle shape of the settle, the back and front. So that creates that stability. But if you were to see which way the liquid would flow, it will flow towards the center, and then somewhere it sort of changes its mind and starts to passes it and flows towards your leg. Okay. So that's the very typical unstable equilibrium, and in linear case there is not much else. So we remember we have everything goes towards the origin exponentially, or everything goes away from the origin exponentially, or this behavior which is both. Okay, so let's look at another model that we haven't had in 2 dimension 2. What is the mutual dynamics of two armies engaged in the most basic combat? And what makes it more basic is the war of attrition. So there is no nothing is happening in terms of there are no, for one, there are no reinforcement, there are no battles or anything. It just pretty much imagine people are shooting at each other. So and then so the size of the two armies is what matters the most, because roughly speaking, the bigger the opponent, the more bullets shot at you, and you're more likely to die. Okay, so if the opponent doubles his army, your casualties double too. Okay, so that's the idea of proportionality. So it's almost shooting is in a manner that almost at random, and then but once again, the bigger army proportionally will cause more casualties. Okay, so once again, there are no inner reinforcements, and so the differential equations are quite simple. Are these. So once again, x and y are the sizes of the two armies, and then once again the loss is determined proportionally by the size of the other army. A and B are positive. Okay, so naturally, when A is equal to B, it means that equally good armies, and then what determines the victory is which one is bigger. That's it. Okay, so certainly before you analyze it the way we have, you could try to analyze and figure out what's happening, but or not. If you have tools, you don't have to think as hard, but just run simulations, and then once you're done with simulation, go with linear algebra, and once again, this is the linear equations with the equation, a linear system, with very simple matrix, Let's do the simulation first. The simulation is along the that line, which is unclear what that line is. It's a simulation. Behaves very similar to what we have seen before, but only with the positive values that we care about. And so there's naturally both of the armies are dying out. Okay, so that's why everything is moving towards left and down. Both the populations are decreasing in size. But nonetheless, where is where is the victories? This is one victory. This is victory for Y. This is Y wins, and here over here X wins. Do not assume that these are going towards zero necessarily, but that's actually the way it works out. So these are the simulations. That's you can already guess that this is an eigenvector or eigenspace. That green line is the eigenspace, right? So we can easily find it by our linear analysis. What's the matrix for the system?
X0, 0,
No, the system of we copy the coefficients of x, y, and of x, y, the four numbers into my 2x2 matrix. So on top left is the coefficient of x in the first equation, which is what? What?
coefficient of X.
In the first equation, yes. So
0.
0, right? And the coefficient of y, -a. In the second equation, the coefficient of x is -b, and coefficient of y is 0 again. So that's a matrix, but it's not diagonal matrix. It's also you have to do a little bit of analysis in order to produce the result. But nonetheless, it's still quadratic equation. So no trouble whatsoever. So once again, the matrix is right here: 0, -a, b, 0. Then we jump straight to go straight to our characteristic equation. Okay, this the characteristic equation said equal to 0. This is a characteristic polynomial, and then we said equal to 0 solve, and then it's very simple result, right? So it is lambda 1 and lambda 2 are equal to plus or minus square root of AB. Okay. So once again, remember what it indicates. It indicates the growth. One will give you population growth, the other one population decay, but which doesn't really make sense. This one makes sense for what we can see, right? We have decay. So it actually, under the circumstances that we have a device here, the death rate is actually the death it will be exponential. Okay, so that's why the second number actually makes sense, because that will indicate the exponential decay that we see in the picture. And the second one is exponential growth because it's positive, which means that it probably will point in the wrong direction. So it has nothing relevant to us. But also, it's good news is also that everything makes sense. It is once again a settle when we on semi-stable equilibrium, and so we have the picture. That similarity with the last example is not coincidental. We can see that the numbers, no matter what A and B are, will give us the picture that we see. Okay, so that's good. We have both growth and decay, but there's no literal growth. So I put growth here. So it's a growth of, if we allow for negative armies inside, then there will be growth, but otherwise it's all decay. Okay, so the eigenvectors are not too complicated to find, so I just jump to the conclusion here. Let me see. So do we really needed to see it? But so for example, So what is it? 0, negative A, negative B, 0. Okay. It is multiplied by my vector xy. It's supposed to produce. Let's take the other one, negative square root of AB xy. Okay, so that's what's supposed to happen, and from this we're supposed to derive values of x and y. So so it's not too complicated because the matrix is so simple. So I'm getting negative ax equal to negative square root of ab times x, and then I also get from the second one I have negative b. I'm sorry, this is the y. This is the y. So I'm multiplying the first row by this one. So I negative a y is equal to negative a b x. And then I have negative bx is equal to negative square root of a b y. Okay, so it's not too complicated. Just substitute into the one into the other. And so what in terms of x, what do I get? Well, negative ay is equal to negative square root of ab, and then negative y over b. Shoot. I wrote the answer without actually presenting the how I found them. So let's just confirm to make sure that it's correct in the first place. So okay, so all right, so negative square root of ab is equal to, what is it, negative a y over x, and also negative bx over y. Okay, so in other words, what is it, x squared over y squared is equal to a over b. Okay. So x over y is equal to square root of a over square root of b. Yeah, okay, so it works out. It works out. So let's just take the this is an exercise. So as you can see, the direction of the vector then of this kind of a behavior, when it is a linear behavior, even though it decelerates, but it goes along straight line, it's determined by what the proportion of a and b. That's its proportion here, right? Because to know the slope depends on what is the slope. The rise or the run, so it will be, what's the slope of the second vector? How do we find the slope of a vector?
Square root of b over square root of.
Square root of b over square root of a, yeah, square root of b over square root of a. Or in other words, b over a square root, whichever you prefer. And so then the proportionality between the quality of your armies, of these two armies, A and B, would indicate which of the armies better, and then the slope might be then depending on if the second army is better than the first, the slope will be steep, right? So B larger than A, it goes like this, right? B is less than A, it will go like that. B is less than, right? So then literally, the larger slice of the XY plane is given to the winning army. Hold on, am I right here? So B over A, B is the second army, and the slope is I'm trying to have an extra logic here beyond the algebra. And like I said, so this is my vector that separates. That vector is separates winning from losing, right? So that vector, this one is so if once again we concentrate on the second arm, if this is y, this is x, then all the solutions, as we know, behave this one. Once again, this is x win. I know this y wins. Y wins, right? So y wins, and over here x wins. So then, as you can see, when they steep, this is steep, and means that the slice where x wins, right, is smaller. That the slice of the quadrant lying above this line, which is the eigenvector, eigenspace. This is the eigenspace. Okay, so then the both of them, if you are on the eigenspace, okay, so what happens? They both winners or both losers, depending on which you prefer, right? So this you end up right here, right? So if the proportional of the arm is just right, the quality is given. Okay, so A and B are given, so the quality of our arm is are given, and then what we're supposed to do here is to find out, depending on the size of the proportional size of the two army, which way it's going to go. And then once again, the line of the eigenspace separates the winning for one from the winning for the other, and depending on the steepness, there will be one bigger than the other. So once again, if the B is larger than A, means that the second arm is better than the first. The slope of that line is more than 45 degrees, which means that that area with the red curve where X win is smaller than the green one at the bottom where Y wins. Okay, makes sense. So even though it is naturally it is an infinitely large quadrant, but nonetheless we split it unevenly, and depending on which army is better, that split may be bigger or smaller. So in other words, the worst army can still win because of their attrition. So even though they lose more, nonetheless they have more to lose, and therefore they can still win. So that's the right one. Okay, so all right. And then the rest of the solutions are here. So once again, that exponential decays that we see so clearly here. Nonetheless, the exponential growth is not as obvious, but it's still present there invisibly. So that's as you can see here. So this is the exponential growth part. A, B, positive. This is growth, and this is decay. Yeah. So in a special case, it's not a special case is follows the second eigenvector towards 0. Yes. Yeah. So yeah. So so that's what it is. We do not see the first eigenvector because it points in the other quadrant, and so nothing interesting is happening there. But this is the direction of the second eigenvector that corresponds to the negative eigenvalue. Okay, negative square root of AB, and that's where there's the decay that is very explicit, the green one. And once again, here the separation is 1 to 3. It appears, maybe, not sure actually the numbers are here now, not quite clear, but as you can see, there's a stiffness that is somewhat, actually it looks like 45 degrees. Anyway, so any questions about this model? Okay, so you can still, the secondary approach is just to do separate equations, then you produce this same result in the manner that's analogous to how we did it with the predator-prey model. So you can actually solve it explicitly in a different manner from this, and but basically you, just like with predator-prey model, remember we ended up with a shape like this. And then it created as its level curves. They were the solutions. They were circular periodic solutions. Okay, in the predator-prey model. Remember that these pictures like this. And here we do exactly the same thing, but the function naturally comes out differently. And that function, instead of being some kind of a like this, like bowl, okay, or cup. Okay, so we have a cell instead. And then if we cut it like this, we know that these level curves of this function will produce the solution, just like with the predator-prey model. So these are those are the hyperbolas. Okay, so just read this. Read this part. So, because if you are willing to deal with Eulers and nothing else, then you can throw in all kind of complexity. So the linear algebra analysis that we have done is out of the window, but the Eulers will stay with us. And so we can throw in reinforcement. We can depends on the size. Maybe a bigger army is able to surround the smaller army, and then they produce the effect of the size might be higher. They might be non-linear. So they're not just shooting at each other nonstop, but rather doing something more fancier in terms of the art of war. So that totally, whatever you make up, you can have a differential equation, and then you will have that the model, so you can do simulations. Okay, so all right, so this one is slightly different. So one more model. Well, no, there's no model, just a differential equation, as you can see here, and no diagonal, not similar. And so once again, Euler method shows this kind of a fancy, fancy convergence. Everything converges, but in a manner that we haven't seen before, or at least it appears to be to do so. But actually, it's still pretty much the same. So the convergence, because once the spreadsheet tells us that the lambdas are -3, -2, so it's exponential decay in all directions. And then one of the directions is clear, the other one is not. Okay, so it doesn't mean that they kind of converge onto each other, not necessarily. And so if we go with the because the eigenvalues are actually different, then it means that actually automatically that the eigenvectors are different too. So one is x equal to y is the eigenspace, and the other one is, and the other one we found here is x equal to y. So it is not perpendicular as we have seen before, but rather these are the eigenspaces. And then whatever happens in between still converges towards the origin in just a manner that's not linear. So once again, read this. So stable equilibrium because everything converges towards it. So just the terminology, so to make it clear what we're talking about, the stable equilibrium, the solution goes towards 0 on one end from infinity on the other end. Okay, so and the exactly opposite on the other end if to have an unstable equilibrium. And then we have when we have exhibited both of the behaviors, if we in case of that's a settle point. Okay, so and then once again, how do we classify it? So without solving and without going to algebra, so what if we have nothing but eigenvalues and eigenvalues produced through linear algebra? What can we say about the system beforehand, before solving it? And the answer is here. So if they are once again real eigenvalues, and that's why we mark it 1, we need the other half roughly. 2 eigenvalues, we have, if they have the same sign, we have a node, stable when the sign is negative, unstable when the sign is positive, and then when they have opposite sides, we have a settlement. That's all. Okay, so that's a simple classification when both of them are real and whether they're equal or not. This one is more interesting because as you can see, it looks very similar like the last one, and we have plotted, but the 2 eigenvalues are actually happen to be equal to each other. Okay, so that's a kind of a transitional case. And so this idea that work, Cauchy polynomial is -1 minus lambda squared. Lambda has to be, both of the lambdas are -1. So just so without any proof, this is how the solution is written. Proportional. So the proportionality is not to the eigenvector because there's only one eigenvector really. Okay, so but rather eigenvector multiplied by t. Well, I have a question mark there. Yeah. Okay. Okay, so I'll just leave it as this, but I do want to point out where the difference lies here. Here's the difference. So rather than having exponential function with the same base, same exponent, okay, so these are the same. So if you were to take two vectors and multiply by the same number, then you have nothing but one solutions on one line, and that's not doesn't give us anything. And so, but rather here we are doing the we're multiplying by t and negative t. Once again, this is c and k lowercase. So so it's a transitional case from discriminant equal to positive, that's above. This is discriminant equal to 0. And the discriminant is negative, it is the complex case, and so we're gonna deal with that next, okay? So, but there is a special case, kind of degenerate between the one generic, the other generic cases, and equal to 0, and that's exhibit behavior. It's not really too exotic, but nonetheless, as you can see, it is still what is it? It is still it's still a node. And it is, in this case, it happens to be a stable node because both of the eigenvalues are negative. Okay, so all right, so and so if we were to take the theorem from last time about linear operators, and then rotation, as you can see, is literally, that's, I'm just repeating the theorem from last time, is that rotation, the linear operator does the rotation through this angle theta combined with rescaling factor, uniform rescaling factor. That's the case, the special case of the negative discriminant. And then so that is kind of productive. So we can say things without complex numbers. So if we can, we take that theorem and let's just do it and see what effect it has. And whenever, and then we complex numbers really confirm how this works out. So so then the rescaling factor is the square root of the determinant. Remember what the determinant was in the first place. It is the scaling factor of the area. Remember, so determinant is equal to determinant is equal to say 4, then you produce either 1 by 4, 2 by 2. You don't know which of the two function produces, but nonetheless it is the resizing factor of the plane. But in terms of the area, if you're doing in only one direction out of the two, then you have a square root. Okay, so that's one dimension at a time. One dimension at a time. For the area, indeed, the area of proper coefficient will be still determined. Well, I got the absolute value here. Okay, so if we take this differential equation, which is maybe familiar, x prime is equal to y prime is equal to negative x, which we solved previously. Yeah, we did solve it previously. Remember, with the substitution, and the end result is x double prime is equal to negative x, which tells us from memory from calculus 1 that what function that you differentiate twice produces the negative of that function. The answer is sine and cosine, and then all linear combination of these two functions. So that's explicit direct solution. So c sine t plus k cosine t. Okay, so that's the solution. But now, suppose we pretend that we don't have the solution. So what do we get from the linear algebra from this theorem right here? And the answer is this Euler. Okay, so we do Euler 2, and that's confirmation, right? Circular motion, sine and cosine, linear combination sine and cosine gives you the rotation, but not necessarily a circle, but maybe an ellipse. Okay, and then the trouble is if we go into actual into our theorem, then we just plug in everything into my equation, and it turns out to be the rotation. What the operator does, it rotates pi over 2. Rotates pi over 2 with rescaling of 1. So there is no rescaling, it's a pure rotation. That's what the linear operator does. So So in other words, if we are here, look at it. So if we're here, this is 0, this is x, this is where we are. So which way does the vector point? And the answer, the other vector, we rotate it 90 degrees, right? So 9 degrees. So if this is x, and we rotate it, which way do we rotate it? We go rotate it. It doesn't seem to match what I have here. I think it should be sine of 1 pi over 2. Oh, why is it my Euler goes? No, it is. Which way is it going? It is going clockwise. Yeah. Okay. Yeah. Pi over 2 clock. So rotation seems to be in the wrong direction. It seems that the rotation pi over 2 theta is supposed to be measured clockwise, counterclockwise. So this is what we're supposed to be doing here. Well, in fact, it's the same exact vector. So x, this is x rotated pi over 2. Oops, rotated pi over 2. Okay, so which is described what? Well, once again, it describes pure rotation because of this proportionality, and so in other words, we're moving always in the perpendicular direction from our location. Okay, so and that is exactly the circular rotation, right? Circular rotation meaning that this is the tangent. Okay, so we are then going off in the direction. There's nothing else that's happening, and so that's the rotation. This is the location. This is the velocity, and then you remember which way the acceleration points. Whoever is taking calculus 3, maybe anyone. Which way does the acceleration point? If this is our next location, then our velocity points in this direction. Okay. So this is my x prime. This is also x prime. And what's happening to x prime? What acceleration is the change of the velocity. Okay, which way do you think is the velocity? Which way is the velocity? The acceleration points.
Same direction as the velocity?
No.
From the tips of the velocities.
If it was, then it would be pointing in the same direction. It would be accelerating along a straight line. So if this is velocity and I'm being pushed from behind, I will be going in the same direction. I will be accelerating, yes, but I will never return.
The tangential and the radius?
No, that's what velocity is, the tangential to the radius.
But the acceleration be between that and the center of the circle.
Right. So, but it means that it points backwards, right? If you think about gravity, that's what it is. The motion of a planet around the Earth, the moon around the Earth, velocity goes along the tangential to the circle, and then the acceleration points in front, and that's Newton for you. The discovery of gravity in a kind of vector environment, pointing the gravity pulls in one particular direction from the object that is moving and to the Earth that actually does the pulling. Okay, so that's all once again discovered through this second derivative, and we assume that we are doing on the first order equations, and so we're not concerned with that. But now we are discovering that, and because the velocity, because the location is the same, the size, the distance of the from the center to our location remains the same. That's rotation, and then which what you once again very brilliant result from calculus 3 is because the distance is the same, the velocity differs, but its magnitude, the speed, is not, which you kind of discover if you are on an orbit. Then you do not the only acceleration that you feel is return. Okay, it's you're not propelled in the forward direction, and then yeah, so and then you discover your force of gravity that points in the irregular direction. So anyway, but it is so awkward in the that formula over here is quite awkward and also unclear where it comes from. So we do need complex numbers in order to explain this, and so we'll spend some time doing it. Okay, let me see. So let's review quickly how complex numbers emerge in our context. That's not how they emerge, but we haven't had any need for complex numbers in calculus up until this very point. Okay, so this is how it happened. We have a system of ODEs, which is simply a function from R2 to R2. Then we linearized it. We didn't discuss it all in the two-dimensional case, but suppose. And so that replaced with matrix multiplication. Okay, so what you see here is matrix multiplication, the second row. So either we are having a linear model in the first place, or we linearized our function, and we are dealing with a linear system. And in order to understand what's going on, we are now looking at the linear operator. The y is equal to a of x. We forget about calculus differential equation for a moment. So A is a 2x2 matrix, and now we need to know what that matrix or operator does. We do analysis with eigenvalues and find these special directions, which unfortunately produce a quadratic equation which might have non-real solutions. Okay, so that's characteristic equation at the bottom. There is no prediction of, because numbers A, B, and C, and D in the matrix could be arbitrary, then there is no say that one is better than the other. Okay, so real eigenvalues, there's nothing special about them. Real or non-real, they're actually equally likely to happen. In the example of rotation around of the Earth around the Sun, or Moon around the Earth, is the example of how common it is to have no matter, even though it is linear. It's not actually linear in case of gravity, but nonetheless, it's very typical to have motion that has non-real eigenvalue. So non-real stands for complex, but really. So let's quickly see that what we already encountered. X squared plus 1 equal to 0 is a quadratic equation that has no solution among the real numbers. So that's number one. Even if you don't have to think about it in terms of the quadratic formula, there is no way for x squared, or real numbers, you square it, add 1, and you get 0. This is simply impossible. There's no requirement for finding it. You can just demonstrate that x squared cannot be negative. Okay, so if a cannot be negative, then you add a positive number, cannot add up to 0. So that's impossible. So if we nonetheless want to make sense of it, then we just write simply square root of -1, and then we imagine that maybe this is a number. We call it a number, even though it's definitely not a number, because up until now, whatever we called a number was a real number. Okay, but it's not. So even though there are no real numbers like that, there's no real number squared gives you -1. Okay, so there is no such thing. X squared is equal to -1. That's impossible. Nonetheless, let's imagine that it works out somehow. So we know that we just confirmed that if x is square root of -1, or plus or minus square root of -1, we plug it into our equation, we do indeed end up with 0. So the algebra applies. That's how we can. It may make up new numbers and nonetheless make sense of it. If the algebra works out, the old rule of algebra, that's what really we care about. All the rules of algebra apply. That's really what the key to understanding new numbers, and it's not entirely new. Remember, you were doing remember elementary school, you're doing the addition of numbers, and then integers, right? And then at some point you learn some rules of how you're allowed to do that, and then they threw it negative numbers, and then you learn that these rules that you learn about positive numbers apply to negative numbers too, and then they throw out fractions. You're still able to apply the same rules. And that didn't stop, unfortunately. Then you got real numbers, right? So you suddenly have square root of 2, which is not a fraction, and then but all the rules of algebra still apply. Okay, so that's, and we are doing one more step beyond that. So once again, from positive integers to add negative, and then the rational numbers or fractions, and then real numbers, and then we just make it one more step to complex numbers. So we make them up, and you gotta say, even though they call them real numbers, but they're clearly infinite. Think about it. Think about the real numbers. You think we're so used to it, but really imagine that what is so special about them? They have infinitely long decimal representations. How do you add two numbers with infinitely long decimal representations? Anyone? What?
Round.
Okay, so the result will be round again. Well, that's the answer is correct, except it's an infinitely small answer, part of the correct answer, because you round, add, then round again, add, then round again, and add, and so you end up with a sequence and of roundings, and then how do you get the answer? The limit of that sequence. Right, so you actually calculus to understand the algebra of the real numbers. Okay, so it's not easy, and even in calculus it doesn't come up with that much. But it is the only way to justify the algebra of real numbers is with calculus. So the calculus of limits, an algebra. Remember, the sum of the limits is equal to the limits of the sum. So that explains why when we deal with the reals, the algebra still applies. The one that we learn initially doing the counting those little things, whatever, in like kindergarten to understand that 2 + 3 is equal to 4 + 1, something like that. And then it turns out that it works with reals, but that you kind of got to go through these long operation. Even the rational numbers. Remember how you learn how to add fractions? That wasn't easy either. Now half of the population can do it. So nothing of that is easy. So we just make it one more step, and now we introduce complex numbers. The good news is here once again that the old rules of algebra will apply. Okay, so that's the good news. So all right, so we introduce an imaginary number, just like which is not, we haven't seen before, hypothetically. So just as you introduce -1, here you introduce 1/2, and then you realize there are many of them. Real numbers, you introduce square root of 2, and then you realize that square root of 3 is also not rationally not and on. You have infinitely many numbers, and the numbers that you add into the picture starts with 1, and then you end up with infinitely many, and then you have a whole you open this Pandora's box. But for now, it's just one number. We call it I. Square root of -1 is I, and then we just declare that I squared is equal to 1, and that's our numerical system looks like this. The real numbers is a line. That's what makes them real. The only reason why we call them real, because they kind of lie on a straight line, and so they correspond to lengths. Okay, so that makes them real supposedly. And then we throw in one more number. Okay, so it's like apples and oranges. So that's the idea. So we can count 1 apple here, 2 apples, 3 apples, and then we will count i's like apples and oranges, and we'll never intermix them. You do not say, well, we have 5 fruit. We still have apples and oranges separately because they are different, and so we will always keep a double count. One for apples and the other one for the oranges. So, but nonetheless, before we build our new numerical system based on these two pieces, all the real numbers in one single extra new number is okay. So these are the facts that we assume that I is not a real number, and including it's not 0. But as I said, it can participate in all algebraic operations with the real numbers by following the same rules as we know. Okay, so addition, subtraction. Even if you don't remember the rules, that's okay, because that's it's fine. And then I squared is equal to -1. That's rule number 3, or assumption number 3 about this special so-called number. So an orange squared is equal to -1. Okay, so these are the rules, by the way. So for example, we have x plus y is equal to y plus x. Same with multiple multiplication. We can factoring, refactoring, expanding, and so on. And we say that that will be also applicable to I. Okay, so which creates right away numbers that are complex. This is what the complex number is. I is an imaginary number, one single number that we made up, okay? But you add a y and now it has a real part and it has an imaginary part. That's combined together. That's what makes it complex. Two different pieces combined together, the complexity of it, assuming that reals are not. So that's once again to remind you, the process you've gone through your study in mathematics from natural numbers to just rational numbers to real numbers, and now we just make it we make it bigger. Okay, so complex. One even bigger class of numbers, that's all. Okay, so x squared minus 1 is x, so this is still true. Remember where that number came from. X squared is x squared plus 1 is x squared plus 1 is what produces equal to 0 produces I. What if we take x squared minus 1, and this one can be factored, and that factoring is comes from the two roots of the polynomial, and so here -1 and 1, and then you can plot that polynomial very effectively like this, because they are nothing but x-intercepts. Okay, if we have a polynomial with non-real roots, then which is plus or minus I. Okay, then if you plot the graph of that function, this is y equal x squared. Okay, it does not have any x-intercepts because x is unreal. Okay, so then you have to imagine that there is a third dimension where this graph does intersect the horizontal plane. Okay, so if it helps. But for now, let's just look at the certain things that are how complex numbers come up. We still get x squared minus 1 is well-known factorization, x minus 1, x plus 1, but x squared plus 1 can be also factored. Okay, so and you can guess what these numbers are. So you can if you want to discover what they are, you just expand. You expand like this, so that they are plus or minus I. X is plus or minus I, and you can confirm x minus I times x plus y I. Once again, we're following the rule of algebra that we have known, and just multiply it out as if I is a number. Okay, so we are not thinking about what it is. We're following the multiplication rule, addition rules. We also I minus I is equal to 0. Naturally, I squared is equal to -1. So that's what happens. That's the crucial part of this computation. This over here, we end up with I squared, and that I squared is actually -1. So we end up indeed with x squared plus 1. I minus ix plus ix cancel out, and then we end up with x squared minus I squared, which is x squared plus 1. So factorization works. That it didn't used to work, now it does. Okay, so because we have more numbers to use, and that's what complex numbers help us with, help us to understand the complex numbers, and then that adds a meaning to the quadratic formula too. Well, later on. And then at this point, there are x-intercepts, but they're not real, so they are still not visible. So that picture is still not, that is not happening yet. So imaginary numbers, once again, they're simply multiples of the imaginary unit. I is the imaginary unit, so multiply imaginary unit by r produces the imaginary number. So for each real number r, there is an imaginary numbers of I, which means how many imaginary numbers are there, and there are infinite many of them already. Okay, so as many. For each real number, there's one imaginary, so they have exactly the same number. Okay, so this is what it looks like. This is so far is our new system of numbers. So we have real numbers, we have imaginary numbers, and once again, apples and oranges. We're counting ones on the green axis, and we count oranges, i's for the second one. Okay, so then once again, quadratic equation can be solved now in terms of imaginary numbers. The quadratic formula a little bit later, but here x squared plus 4, if we need to solve it, we just write x equal to plus or minus square root of -4. We factor 4 out, okay, because like I said, all the rules apply to the numbers, and I end up with plus or minus 2i. Okay. So, and then, so imaginary numbers are the laws of algebra as we know them. If we need to simplify the expression, we try to manipulate it in exactly the same way as before we would with the real number. Okay, so, all right, so, another way to see it is either apples and oranges, or you're just doing algebra with x's and y's. So you don't mix x's with y's. That's how we do it, inches and pounds. Okay, so I'll stop here and I'll see you next.